welcome back. Today we're going to look at sort of a next evolution of the theory we're looking at. We've basically mastered cost functions, given a bit of code, make a function for how many steps that it takes, how long it takes to run, and now we're going to get a little bit more advanced. I also mentioned near the end of last class that something very important in this sort of theory is the notion of comparing functions. Like if you have one algorithm whose cost function is like 3n plus 3 and another one whose cost function is 2n squared, which one will take longer? So that's what we're going to be looking at using a tool called asymptotic notation. And it's kind of going to formalize the stuff in this slide. We have a sort of hierarchy of functions. We say that any constant function, so any function that has the same output value for any input, we say that it's strictly smaller than any logarithmic function, which are strictly smaller than any polynomial, which are strictly smaller than any exponential function, which is strictly smaller than factorial, which is strictly smaller than this absolute mess, this evil thing at the bottom of the slide. We're not going to look at n to the power of n. Algorithms that take n to the power of n time are extremely rare, thankfully. And you may notice that this doesn't really hold up formally. A constant function can't directly be compared to any of these. And we also have occasions where we have exceptions to the rules set out here. Like, I'm pretty sure the square root of n is greater than n for values of n from 0 to 1. So all this stuff is not strictly reliable. It wouldn't get you marks on assignments, and it definitely wouldn't let you publish any papers. And yet, it's a good idea to have a algorithm that takes n squared steps is probably going to take longer than an algorithm that takes n steps. So it's worth formalizing this into something that we can definitively say is true or false for certain functions. We can somehow definitively say that one function is greater than another. Hopefully you've read the readings for this week. As usual, I'm going to give short introductions for new concepts that were shown in the readings, but I'm not going to give a very thorough introduction. Probably not a very good introduction. But if you've read the readings, then everything I say will build naturally on it. So, say you have an algorithm that receives an input of size n. That could be just a number n, but is probably something like a list with n elements. This algorithm has a cost function f of n measured in steps, and f of n is in big O of n cubed. And we want to figure out what that means. Informally, it means that it's like in the same order of n cubed. It's going to be a polynomial with a term n cubed, polynomial of degree 3. But of course, this is math, this is theory. We got to back it up with some sort of specific statement that can be shown to be true or false. So it might mean that the algorithm takes exactly n cubed steps for all n greater than or equal to 1. That's definitely incorrect. neither is option B, or really any of these options. You're looking at the same slide as I am. The answer is none of the above. Options A through D are all decently good guesses of what it means for a function to be in big O of n cubed, because it basically means that it's similar to n cubed. But the actual definition is none of these. It's going to be more complicated than all of these. And they're given here. So this is finally the start of a computer science related justification for the weird proofs with inequalities and quantifiers that we've been doing. They've all been building up to the idea of comparing functions. So if f of n is in big O of g of n, then there exists an m greater than 0 and an n naught greater than 0, such that for all n greater than n naught, f of n is less than or equal to m times g of n. Wow, that's a lot of symbols. Probably not much actual meaning. Again, this was in the readings, but I'll do a quick sort of demonstration of what this means. And it's a demonstration that I highly recommend replicating when you're studying on your own and doing assignment questions like these. Throw your stuff into a graphing calculator. So let's say we want to show that n squared is in big O. Wait, we would need like a specific function. Let's say n squared is in big O of 3n squared plus 1. Since this is Desmos and it works with real numbers, the convention that it requires you to use is to use x instead of n. You'll have to make that translation in your head. So I think I said 3n squared plus, I'll be real with you, I have no idea what number I said at the end. I'm going to say 2. Hopefully I said 2. So intuitively, we can see that the purple function x squared is always less than the black function 3x squared plus 2. And that as you zoom way, way out, they both grow at similar rates. And I guess this is inadvertently like the easiest possible example I could give of showing that a function is in big O of some other function. Because to fulfill the definition of big O, you need to find m and n naught such that for all n greater than n naught, f of n is less than or equal to m times g of n. And for this example, we can just choose m equals 1. So the function that the other function is in big O of isn't being multiplied by anything. And set n naught to 0. So it's true for all positive n. Not a very interesting example. I'm going to try and think of a better one. Okay, so this time we're going to say that 3x minus 10 is in big O of x, or n, whatever letter I used. Looking at the graphs directly, we can clearly see that 3x minus 10 is greater than, okay, I'm confusing myself with the x's versus the n's as a convention, establishing this right now. I'm just going to use x when Desmos is involved. We can see that 3x minus 10 is greater than x after a certain point, somewhere like 5. And that would go against the definition of big O. So it looks like 3x minus 10 is not in big O of x. But remember that the definition is not that 3x minus 10 is always less than x. It's that it's always, or eventually always, less than some constant multiple of x. So I set m to 4, and now we could see that now we can see that 3x minus 10 is consistently less than mx. Goes on like this forever. And that it starts being less than mx. Starting at like some negative number. So if we were proving that 3x minus 10 is in big O of x, we choose n naught equal to 0 and m equal to 4. Of course, many different values of n naught and n and m are valid. And I don't know about you, but I'm finding these examples a bit frustratingly vague. I don't think it's quite justified why we want to compare functions like this yet, and it's especially not justified why we're using these complicated definitions, big O of n and big omega of n, which I haven't even covered yet, instead of the more intuitive idea of like f of n tends to be bigger than g of n, or something like that. So hopefully I do my job. Hopefully all these make sense as to why they're used by the time we finish covering them, but it's going to start out a bit mysterious. Before I move on from this slide, it's worth noting these like analogous bits. Saying that f of n is in big O g of n is like saying that f of n is less than or equal to g of n. Likewise, big omega is like saying greater than or equal to. We're going to see alternate definitions in later lectures that are analogous to other comparators. So strictly less than, strictly greater than, and equals. And the rest of this lecture is going to be examples. Like I said, the more abstract proofs with inequalities and quantifiers have built up to the proofs of asymptotic notation to be seen here. So here we're going to use the rounding up trick. And the procedure is almost exactly the same as we've seen before. Of course, there's a bit of an indirection here. We don't have an inequality immediately given to us, but we're using that big O notation. So a good first step when solving any of these questions is to just write out the inequality that writing out the statement that you're going to try to prove expanded. Do this. I'm going to do it. So we're trying to show that there exists an m greater than 0 and an n naught greater than 0, such that for all n greater than n naught, n3 plus n plus 1 is less than or equal to n to the power of 4. Cool. Next, our rough work happens. We're going to start with the inequality that we want to prove, and then attempt to sort of reverse engineer it. Oh wait, meant to put constant multiple here, n, or m. So we're going to try to solve the inequality for any of the variables that were existentially quantified. In this case, we're going to solve for m, and along the way, make assumptions about n being greater than certain constants, and then just remember those constants and use them to set n naught. So we're going to simplify the left side. And this one's actually pretty simple. We're going to use the hierarchy of functions detailed earlier in the slides and make some statements that actually are true all the time. You can't always rely on the hierarchy of functions because it has exceptions like the thing I mentioned with square root of n and n. But the things I'm about to say are always true given the constraints we're going to put on n. So I know that I want to turn all these terms into n terms with the same exponent. So I know that for all n greater than 1, n cubed is strictly greater than n squared, strictly greater than n, strictly greater than 1. So I can just guess n probably equals 1. And from that, it follows that n is less than n cubed, so I can just replace it with n cubed. And also 1 is less than n cubed, so I can replace that with n cubed. So now I have a much nicer inequality. 3n cubed is less than mn to the 4. But actually, on a second look, this doesn't quite allow me to solve for m. Remember, I'm trying to solve for m, not n, due to the quantifiers. If I tried to simplify this, I would end up with something like m is greater than 3 over n, which wouldn't be valid because of the order of quantifiers. M is defined before n, so any definition of m that uses n would be nonsensical. So take a moment to think, what would this inequality need for me to be able to easily solve for m and just eliminate n? I think it would be real convenient if both of the exponents were the same, and then I could just divide both sides by n cubed or n to the power of 4 and end up with m greater than 3. All right, this should be less than or equal to, because we're keeping the inequality from before. So I'm just going to revise my inequalities a little bit, use the hierarchy of functions even more. Note that n to the 4 is greater than all of these. And then we could just make replacements as before. Individually, n cubed is less than n to the 4, n is less than n to the 4, and 1 is less than n to the 4. And it continues to be true when you add those up. We get 3n to the 4. And then we could just cancel out those two n terms. So we have m has to be greater than or equal to 3, and n has to be strictly greater than 1. And that's exactly what we see in the formal proof. We start off by letting m be equal to 3 and n naught be equal to 1. And then show that for all n greater than n naught, in this case n greater than 1, the inequality is true. And the last step is basically just our rough work in reverse, manipulating the inequalities to change each term to n to the 4, adding them up together, and you get the other side of the inequality. It's all great. Going to switch over to the graphing calculator again to show off this example graphically. Okay, so we see that the purple function x cubed plus x plus 1 is eventually less than x to the power 4, the black function, and it seems to continue that way forever. So we actually could have chosen n equal to 1, since it wasn't actually necessary to make a constant multiple of x to the 4. Like, we didn't need to sort of contract it to make it true. So this sort of illustrates a point that I'm going to make over and over again. With these sorts of proofs where you have to choose a specific value for certain variables, there are many correct choices. M equals 3 was true here. And we saw from the graphing calculator that m equals 1 would also work. Of course, you wouldn't get any marks from handing in a printout of Desmos. The marker would go like, oh, but what if the purple function actually moves above the black function at some point? I don't know. It probably won't happen, but your job as a student, aspiring mathematician, is to prove that the purple function will always be less than or equal to the black function. Interestingly, the point where the inequality that we want becomes true is like 1.6803. That's probably some square root or fractional exponent. I don't know. If you were starting with the graphing calculator output and then trying to make a proof, you would say let n naught equal 1.61803. And then I guess you'd attempt to do the algebra from there, starting with one side of the inequality and working to the other. Remember that this stuff, all the stuff on this slide, and the graphing calculator are both valid methods of doing the rough work to find the values that you need to use in a real proof. It's just that the techniques we're learning about in this class give you much nicer values. Once you get through the drudgery that is the rough work, proving the statement with n naught equal to 1 will be way easier than proving the statement with n naught equal to 1.61803. All right. We're going to show that 3n squared plus n is in big O of n squared. I'm going to do the graphing calculator first, mix things up. Okay, so we've graphed the two functions. We see that 3x squared plus x seems to be consistently greater than mx squared. And that's not what we want. We're trying to prove that after a certain point, 3n squared plus n is always less than mn squared. So how do we reconcile that with what the graphing calculator is telling us? Well, we're just going to have to choose m smartly. Wow. M plus 7 seems to work, or m equal to 7. That would also give us n naught of 1/4, 0.25. Sure. But I'm going to go and do the thing that I actually recommend doing. Start by rewriting the thing that you're actually trying to prove. After you've done that, rewrite just the inequality. And then solve for existentially quantified variables. In these big O proofs, you're always going to be solving for m while finding constraints on n. We have a complicated side of 3n squared plus n. Sure would be nice if n were less than n squared. so that I could combine those two terms. This is true when n is greater than 1. Wait. And then you bring the simplified side back into the original inequality. And the algebra from there is pretty easy. We find that m has to be greater than or equal to 4. And that n has to be strictly greater than 1. Let's see if the calculator backs this up. Oh, look, starting at 1, you could just barely see it, but after that cutoff, the inequality that we want to be true is true. And it continues like that forever. So then the usual reversal of rough work ensues. You start by naming the values that you found at the end of your rough work. Then you take one side of the inequality and use the values that you chose to show that the inequality that you're given at first is true. In this case, it sort of does the rounding up trick here, which we get from n being greater than 1 and thus n squared being greater than n. And then the value of m we chose is just there. It's 4. It's chilling. Okay, now we're going to see an example of big omega. So this time, the function here is in big omega of this. 6n to the 8 minus 3n squared is in big omega of n to the power of 8, which intuitively means that 6n to the power of 8 minus 3n squared is greater than or equal to n to the power of 8. We're going to expand the definition. If the next example isn't an example of something not being in big O or big omega, I'm going to skip it, because I really want to show off something not being in one of these families. If we were to plug this into a graphing calculator, we'd be a little confused at first because the minus n squared is probably going to result in the function on the left being less than the function on the right, but a smart choice of m will resolve that. I don't think we actually have to rewrite this inequality again. I'm going to skip straight to simplifying the complicated side. And this is going to use the factoring out trick that we learned in an earlier class. Factor out the largest power of n, and you'll be left with some number minus some fraction with a smaller power of n in the denominator. And then you choose a constraint on m that makes it so the thing in the brackets turns into a nice constant, and then you have a simplified inequality. Before, we would choose n such that the fraction is 1/2 because we are subtracting from 1. But since the thing we're subtracting from is greater than 1, now it's even more convenient to choose an n such that the fraction is equal to 1. So then we just get 6 minus 1, 5. As long as the result is like an integer or an easy to understand fraction, we're good. So if n is greater than 3, then n to the power of 6 is way greater than 3. So 3 divided by n6 is going to be less than 1. Which means that if you subtract that thing from 6, the result is going to be greater than 5. Note that here, I didn't use a question mark as I usually do. I'll write something like that just to make things consistent. I'm guessing here that n should probably be greater than 3. Other values would certainly work. Oh, good heavens, how are we going to solve this one? Woo! I kept forgetting to put the or equal to part there. We end up with an inequality saying that m has to be greater than or equal to 5, and one that says that n has to be greater than 3. So because of that, we choose m equal to 5. Anything greater than or equal to 5 would work. And n naught to exactly 3 to ensure that using the quantifier n greater than n naught, we end up with something greater than 3. Yeah?
So if 5 is greater than or equal to n, then how do we get n is greater than or equal to 5?
Because I used the wrong inequality sign. Thanks for pointing that out. Yeah. So then we start with the values that we chose, start with one side of the inequality, and make it to the other. As always, a good way to study these proofs is to look at that last step with the inequalities and make sure that you understand all of the steps. This factoring out step should be immediately understandable. It's just factoring out. But this greater than step is not immediately sensible. And it'll take some turning of the gears in your brain to remember that 3 over n to the 6 turning into 1 comes from this sentence. And then, of course, when you're writing your own proofs like this, make sure that every step of your algebra is either like immediately obvious, true for all n and m, or that it's justified by something else that you've written recently in the proof. Okay, 2n to the 5 minus 7n to the 3 is in big omega of n to the 5. Well, I said earlier that if we're not checking out a negative result next, I'm going to skip it. So I'm going to skip this. And this. Oh, phew. And I think this is, oh yeah, one of the last examples. I think that if I finish the lecture like well before the end of the class, I'll go back to those earlier examples. But for now, I want to skip them because showing off an example of a function not being in one of these sets is pretty darn important. So 3n to the 5 minus 10n is not in big O of n cubed. What does that mean? Well, you could use the intuition that big O roughly means less than or equal to. This is saying that 3n to the 5 minus 10n is not less than or equal to n cubed. So strictly greater than? Kinda. We have to negate the definition of big O and then prove that the negated statement is true. So negating the definition gives us for all m greater than 0 and all n not greater than 0, there's a specific n greater than n naught such that the opposite of the usual inequality is true. So let's graph this. Cool looking functions. Oh, and I'm going to set m to 1 to start. So a usual big O statement, like 3x 5 minus 10x is in big O of x cubed, would mean that eventually 3x to the 5 minus 10x is always less than or equal to some constant multiple of x cubed. But the opposite of that means that no matter what constant you try to multiply x cubed by, and no matter what starting value n naught you choose, 3x to the power of 5 minus 10x will always be eventually greater than mx cubed. So with m equal to 1, we see that this happens immediately. 1.414, ooh, I think that's the square root of 2. Neato. So let's attempt to show or to make some rough work showing that 3x to the 5 minus 10x actually is in big O of x cubed. Yeah, x cubed. That would involve setting m so that I'm getting my inequalities mixed up. That the purple line is eventually below the black line. So I set m to 10, massive value, and it looks like our job is done. We've successfully shown that 3x to the 5 minus 10x is eventually less than mx cubed. We showed that it's in big O. Amazing. Congratulations. But if we scroll up and up and up and up, we see that eventually 3x plus 5 minus 10x overtakes mx cubed. So maybe we could choose an even bigger number. I'm not sure if I'm actually going to be able to scroll up far enough to prove my point. But eventually, the inequality that defines big O, that 3x to the power of 5 minus 10x is less than or equal to x cubed, will become false. Yeah, I'm going to stop scrolling up, but trust me, it works. And then, correspondingly, algebraically, it means that if you attempted to start rough work for a big O proof, started with 3n 5 minus 10n is less than or equal to mn cubed. If you started with the inequality used for big O proofs, and then you attempted to find a specific value of m and constraints on n, it'll just never work. For any m and n naught that you attempt to choose, there will exist an n greater than n naught that will mess up your inequality. So let's prove this. We have our inequality, and we have different quantifiers from last time. Now, since m is universally quantified, we're not going to choose a specific value of m. Likewise, we're not going to choose a specific value of n naught, but we are going to choose specific n. Moreover, since n is defined after these other variables, our value of n can be, or the value we choose for n can use the other variables. Bit of a spoiler, we see that the formal proof actually uses the other variables to define n. But like all things, it starts with trying to simplify the inequality so that we can actually solve for the variables that we want to, which means taking 3n5 minus 10n and turning it into something that can be more easily compared to mn cubed. In general, a subtraction symbol is kind of, sort of a giveaway that you're supposed to use the factoring trick. This is not always true, but it's true pretty often, and it's true here. Factor out the largest power of n. Now we want to choose n such that 10 divided by n to the 4 is convenient. Convenient enough that 3 minus 10 over n to the 4 is something that, or it's just some positive constant. So, try and guess what I'm about to do. It's very similar to the last rounding up trick, bit of rough work that we did. I'm going to say n should maybe be greater than 10 to allow for n to the 4 to be way greater than 10. Actually, I'm going to write it a bit differently. This hopefully illustrates better why saying that n has to be greater than 10 lets us say that n to the 4 has to be greater than 10. 10 out of 10. Oh, right, yeah. I was panicking a bit because my tried and true methods were failing me. I had found a simplified inequality that's greater than the original, and I want to put it in between the two sides of the inequality that we were originally trying to prove, but that wouldn't work with that symbol. 2n to the 5 is less than the original. And because of this, and I must apologize yet again for the lack of satisfying explanation for this, we have to put the simplified side of the inequality in between the original sides. A slightly better justification for this than the ones I've given before is that it has to be in the middle of the original inequality in order for this big chain of inequalities to work. We're going to have the original sides on the far sides of the inequality in our proof, and the simplified side somewhere in the middle. So yeah, all of math is broken, or I don't know what I'm doing. Woo! But I remembered we're not trying to show that 3n to the 5 minus 10n is less than or equal to mn cubed. That is false, at least for the quantified variables that were given. We're showing that it's strictly greater than. So the rough work that we did does find a simplified side that fits in between the original sides, and we're good. So I hope this is a bit of a teachable moment. Be very careful about the definitions that you're using and the negations of them. It's way too easy to accidentally flip an inequality and go off on a wild goose chase proving something that isn't true. And also, your first attempt at these things will probably be wrong. So double check your work. So anyway, I think we have 2n to the power of 5 is greater than mn3. Wait. Oh yeah, I think we will want to simplify the inequality a little bit more in order to make it possible to solve for n. Because if we just divided both sides by n cubed, we'd end up with like 2n squared is greater than m. Actually, this would totally work. N squared is greater than m over 2, and then n is greater than square root of m over 2. Sure, that works. But it's nothing like the value of n shown in the formal proof on the slides. So I'm going to keep saying it. There are many different values for existentially quantified variables that work for proving these statements. Choosing any n greater than square root of m over 2 would work. But I'm going to do my best to reverse engineer the original solution. And to do that, I think we can just take advantage of the hierarchy of functions, assuming that n is greater than 1, which is true, because we said so. This whole thing is greater than 2n to the 4. We can just do that. Another thing that we can just do is take away that pesky 2. And we end up with an even simpler expression. This is part of what I was talking about when I first introduced these concepts, saying that your brains are all used to working with equal signs through your entire mathematical education so far, and that inequalities are going to be really weird in comparison. This whole thing is an example of that. You can just drop terms that you don't want as long as it works with the inequality that you eventually want to prove. So, take 2 of solving for n in the simplified inequality. This one's real easy. Ta-da! Isn't that so much more aesthetically pleasing than n being strictly greater than square root of m divided by 2? Like I said, though, any n greater than square root of m over 2 will work, and m is greater than square root of m over 2. Therefore, it works. So, how are we going to choose our variables? We have that m and n naught are arbitrary. We say that. And then we have several constraints on n. The statement itself says that n has to be greater than n naught. We'll remember that. We found in our first bit of algebra that n has to be greater than 10. And then we solved for n, finally, to find that it has to be greater than m. So let me just write those down. N has to be greater than n naught. N has to be greater than 10. And n has to be greater than m. How do we satisfy multiple constraints? We use the max function since all of these constraints are n being greater than something. If all of these constraints were n being less than something, you'd use a min function. And if you have a mix of less than and greater than, I can't help you there. You're in trouble and you probably did something wrong. So to reconcile all this, and to choose a specific value of n, since that's what the quantifier said that we had to do, we're going to use max n naught, 10, and n. We're not done yet, though. This setting of n will guarantee that, it won't even guarantee this. It'll hopefully make it so n is greater than 2 out of these 3 constraints. But by the nature of the max function, it's going to be equal to one of them. And thus, the condition that it has to be strictly greater than that one isn't going to hold. So we need to do something else. The formal proof here it adds 1 to each of the options. And it doesn't seem to add 1 to 10, which might be a mistake, but is more likely to be just clever observations of inequalities, finding that n being greater than n naught and m somehow guarantees it being greater than 10. We're not going to worry about it because I have a more elegant way to guarantee it. You just add 1. So it's going to be greater than or equal to all 3 of those, and then you add 1, you get n being strictly greater than all of the constraint values we found. Wow. So in general, you're gonna want to do rough work until you end up with an inequality that's just solved for a variable that is defined existentially. Sometimes you'll only have 1 or 2 constraints on your variable, or sometimes you'll only have 1. Other times you'll have multiple. And when you have multiple, use the max function. That was the takeaway from this example. And then I think there's nothing else new in this example. You do some algebra to get from one side of the inequality to the other, thus proving it for real. Some steps of the algebra are relatively simple algebraic manipulations. Other parts may seem to come out of nowhere, but are justified in the previous step, something like this. And you should definitely sink your teeth into the inequality and make sure you understand all the steps. So we got 13 minutes. I'm going to do one more example. You'll have to give me a moment to figure out which one to do, because I want to try and figure out which one is most helpful for me to go over. Oh yeah, I think one of the earlier examples involves a new trick, so I should definitely show that off. This one's just factoring, and right, draw unneeded terms. This is another example of inequalities occasionally making things really easy, and how you can just sometimes just choose to drop parts of an expression that you don't want to have. So in this case, we're trying to show that 6n to the power of 8 minus 7n squared is in big O of n to the power of 8. Intuitively, is less than or equal to that. And by definition, we have all these quantifiers and inequalities. So let's try to reverse engineer the inequality that we were given. As usual with proofs that a function is in big O of something else, we're going to solve for n while noting down any assumptions about n we made along the way. And we have one side of the inequality that has 2 terms, and we want to simplify it by turning it into an expression that fits into the middle of the original inequality. So 6n to the power of 8 minus 7n squared. Again, we want to simplify this to something that is greater than the original side, so it can fit like right here. So how do we do that? I guess we could probably use the factoring out trick. Wait. Yeah, this would probably work. You choose n greater than 7, thus n to the power of 6 is greater than 7. Thus, 6 minus 7 7 over n to the power of 6 would be less than. Wait. Oh yeah, I don't think it would work. Oh well. That was supposed to be an example of you could maybe do this, but it would be too complicated for what it's worth. But it turned into you could maybe do this, but it would be wrong and wouldn't get you anywhere. I guess a stronger version of the point that I was trying to make stands. Enough beating around the bush. I'm going to simplify this. Check this out. I did it. If n is positive, in fact, I think we could change this to n greater than 0. As long as n is positive, then 7n squared is going to be positive. And then anything minus 7n squared is going to be less than that thing not minus 7n squared. We can, as long as the inequalities still work, they still check out, you can just drop terms that you don't want to work with. So be on the lookout for opportunities like that, because sometimes we'll be forced to use more complicated techniques. We weren't able to just drop 10n from this example because it wouldn't work with the inequality sign that we wanted to show an inequality for. But this time we totally can. So 6n to the power of 8 less than or equal to m to the power of 8. We end up with m greater than or equal to 6. Accordingly, we choose m equal to 6 and m greater than 0. This proof uses n not equal to 1. I like that. It's the smallest integer that is strictly greater than 0. But I suppose if you really wanted to, you could say let n not equal 0.0000000001, and it would still work. Let's see. Oh yeah. Since the rough work was pretty simple, the formal proof follows that. And to expand this slightly, actually I can't, oops, oh, come on. Yeah, I can't even expand this. It's just immediate that something minus a positive expression is going to be less than that thing not minus the positive expression. It's cool. So this stuff is usually complicated, but be on the lookout for cases where you could make it simple. Just make sure that the inequalities all check out. Okay, 5 minutes left. Don't get going quite yet. I feel like there was an assignment clarification that I want to make, but it's escaping me. If it turns out there was something important I wanted to say, I'll make an announcement about it. But I'm starting to suspect that the thing I was trying to remember to do was to cancel office hours for today. Is there anything I could do in 5 minutes? I guess I could point out that in here, you can't do the drop unneeded terms trick because of the inequality. But if this were an addition, you would totally be able to say that 2n to the 5 plus 7n3 is greater than or equal to 2n5, and then that would be really easy to compare to mn5, but you can't do that because this is subtraction, not addition. So it looks like I've done all these except one. I think I will leave it at that. Next class, we're going to look at more asymptotic notation. The big O and big omega that we've seen so far correspond to less than or equal to and greater than or equal to. So next up, we'll be able to find a formal way to say that a function is strictly less than another one, strictly greater than another one, or equal to that. All right, I'll see you all tomorrow. Oh, good heavens, I wanted to talk about the quiz. Sit back down. Okay, so you don't have to memorize this. That was the clarification that I wanted to make. There will be a question on the quiz that is matching definitions to terms. So you'll have to fill in blanks or draw lines to say that big O is that, big omega is that, and the things that we'll learn about next class correspond to the definitions we'll learn about next class. So you don't have to memorize these, but you have to understand them well enough to recognize them. Okay, that's it for real. Bye.